Who are we? What is everything? Why is everything? We all often ask these questions while going through an existential crisis. Well, there are many different answers to these questions. Some philosophers might say that we all are just butterflies who are dreaming of being alive. Religions might have their own explanations. But we are not here to talk about that. We are here to talk about the explanation which science gives us. We all have been taught that everything is made up of atoms which have electrons, neutrons and protons. But what if I tell you we all might just be strings? When Isaac Newton was sitting under a tree, an apple fell on his head. He asked himself, why did the apple fall? And that question led us to a concept which we now know as gravity. Although Newton answered how gravity works, he was unable to answer what exactly causes gravity or how does gravity transfer in space. That was the question which Albert Einstein picked up. In his incredibly famous theory, the theory of relativity, he explained gravity as a curvature of spacetime. Imagine a bowling ball is placed on a trampoline. This ball creates a dip on the fabric of the trampoline. You can relate the fabric of the trampoline to spacetime, a concept which combines space and time into a single entity, and the bowling ball as the mass of an object. According to Einstein, objects don't experience gravity as a pulling force. Instead, they follow the curved path created by the wrapped spacetime. Let us understand this with a visualization of planets and stars. The mass and the energy of the Sun causes the spacetime around it to curve. Earth experiences this curvature of the spacetime around the Sun and follows the curved path around the Sun. Similarly, Earth has its own mass, therefore curves the space-time around itself, and the Moon follows that curved path. This concept is known as gravity. Everything that you see creates a curvature around itself. Your devices, your water bottle, the vehicles that you see, even you yourself cause the space-time to curve. But then the question arises, why do other things not get pulled towards you and follow the curved path? Imagine an ant on a trampoline. Will it cause the trampoline fabric to bend? Yes, it will. But will the effect be seen with naked eyes? No, right? Because it is way too small. Similarly, your mass or mass of the objects that you see around yourself is very small compared to planets or stars, and therefore the effect of curvature is negligible and it cannot be detected with our current technology. More massive an object, the greater curvature it creates in space-time. For example, Jupiter creates greater curvature than Earth and hence has a stronger gravitational pull. Einstein also explained the concept of time dilation and gravitational waves. Time runs slower in region of stronger gravity. This is known as time dilation. General relativity also predicts the existence of gravitational waves, which are ripples in space-time caused by accelerating massive objects. These waves were recently confirmed by scientists. General relativity is a very powerful theory, but it remains incompatible with quantum mechanics. Seeing the success of Einstein's general theory of relativity, many physicists tried to incorporate electromagnetism to present a unified theory. One such theory was given by Kaluza and Klein. Just like the 2D plane is a part of a larger 3D space, the Kaluza-Klein theory proposed that our 4-dimensional spacetime, which consists of 3 spatial dimensions and 1 time dimension, is actually a part of larger 5-dimensional space. Kaluza showed that by including this extra dimension and reformulating Einstein's equation of general relativity in this 5-dimensional space, one could naturally get the equations for gravity in our four-dimensional world. In fact, electromagnetism seemed to emerge as a natural consequence of the geometry of this extra dimension. Kaluza-Klein realized that the extra dimension proposed by Kaluza was likely very small and curled upon itself. This curled up dimension was much smaller than an atom, making it undetectable with our current technology. This concept is known as compactification. Let us understand this by an example. When we see an electric pole from far away, the wires seem like a straight line. But when we see those same wires from perspective of an ant, the ant can see two dimensions, the straight long one and the curled up circular dimension. No doubt the theory was good on paper, but it lacked physical interpretation. What was the nature of this fifth dimension? Why was it so small? What were its properties? The theory was a classical theory and therefore incompatible with quantum mechanics. From this point onwards, a search for a unified theory began. Many physicists, even Albert Einstein himself, actively pursued the idea of unified theory, a theory which explains gravity, electromagnetism, and quantum mechanics under a single framework. Later, in 1932, a scientist named James Chadwick discovered neutrons, which confirmed the idea of a positively charged nucleus inside the atom, consisting of protons and neutrons. But there was one problem. We all know the nature of electromagnetic force. Unlike charges attract, and like charges repel, right? So, which force was holding the nucleus together? This question led to the introduction of a new character in the story of forces, the strong nuclear force. Strongest of all the four fundamental forces which we know today, it's responsible for binding protons and neutrons tightly together in the nucleus. Without this force, the positively charged protons would repel each other due to electromagnetism, tearing the nucleus apart. Around the same time, scientists observed some reaction inside the nucleus of an atom, radioactive decays, which changed the fundamentals of a subatomic particle. In contrast to the strong nuclear force, a weak nuclear force is what causes these decays. As the name suggests, the weak nuclear force is much weaker than the strong nuclear force, but it plays a crucial role in certain types of nuclear decays. The discoveries of strong and the weak nuclear forces made unification of the fundamental forces even harder. So the question still remains, what are we made of? What is the true nature of reality? The theory of everything. To understand the true reality of nature, we need to zoom into matter. Suppose we have an apple. When we see inside an apple, we find atoms. For a long time, we believed that atoms were the fundamental, indivisible building blocks of matter. But we were wrong. When we zoom inside an atom, we find electrons revolving around a nucleus. Wait. What is this nucleus made of? Neutrons and protons. You may think, that's it, right? Here's where things get interesting. When we take a neutron and see inside it, we find tiny little particles, which we call quarks. That means protons and neutrons are not fundamental particles. They are made up of quarks. There are 6 types of quarks, each with a specific flavor: up, down, charm, strange, top, and bottom. These flavors differentiate them based on mass, electric charge, and other properties. This is where the conventional idea ends. Currently, if we take a deep dive inside quarks, we find nothing. But there is more to the story. Remember, I told you in the beginning, we all might just be strings? Well, there is a very famous theory in physics known as string theory, a potential candidate for the theory of everything. Though not yet proven, string theory suggests that quarks are made up of tiny little strings. These strings are like strings of a guitar. Just like a guitar, these strings vibrate in different patterns which corresponds to different particles and forces which we observe in the universe. For example, a particular vibration, let's say vibration A, corresponds to particle A. There is a different vibration, let's say vibration B, which corresponds to particle B. String theory offers a fascinating perspective about the four fundamental forces. The theory proposes that the vibrations of strings in additional dimensions beyond the familiar four-dimensional spacetime are responsible for gravity. The specific way these vibrations interact with spacetime creates the effect which we know as gravity. It also proposes that electromagnetism, the strong nuclear force and the weak nuclear force arise from different vibrational modes of the same fundamental string. But every good theory faces some challenges. According to bosonic string theory, the original string theory in which strings were made of one type of particle called boson, the universe has 26 dimensions, 10 spatial and 16 time dimensions. It says that the rest of the dimensions are curled up. This high dimensionality poses a significant problem. But you might say, Jagrav, there are only 4 dimensions, 3 which we can see and 1 time dimension. Well, yes, you are correct. Explaining why the extra dimensions are unseen is a major hurdle for this type of string theory. But wait, it's not over yet. There is another type of string theory which tried to tackle this problem, the superstring theory. Superstring theory was developed to address some of the shortcomings of the bosonic string theory. It introduced a new type of particle, the fermion, along with the bosons. This additional symmetry, called supersymmetry, offered potential solutions to some problems. Superstring theory requires 10 dimensions, 9 spatial and 1 time dimension, which is a significant reduction from the previously stated 26 dimensions. But why does string theory have extra dimensions? These extra dimensions are required for the mathematical consistency of the theory. Vibrations of strings in these dimensions are believed to correspond to different particles like neutrons, protons, electrons, quarks, which we observe today. But the mystery still remains. Are there extra dimensions? If yes, where are they? Are they curled up or compactified? Too small to observe with our current technology. Einstein was fascinated by the idea that a single theory would explain all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force and the weak nuclear force. The dream of unification, which Albert Einstein and many other physicists saw, still remains incomplete. Is there a theory of everything? The question still remains unanswered. Who are we? What are we? And why is everything? If you watched till the very end, comment strings and let me know. If you learned something new, do like the video, and to watch more such content, please subscribe. Thank you.